Hello and welcome to Adding Energy. I'm your host, and on this we're going to talk about energy efficiency, energy issues, and energy usage. Today I want to talk to you specifically about laws. There's different kinds of laws. So there's the law of gravity, there's the first law of thermodynamics, there's the law of conservation of energy and mass, and those laws are laws you can't break. You're stuck with those. If you can break them, great. Give us a call and we'll fly a lot cheaper. There's other laws, like how high a light switch needs to be. Now, that might not seem important, but sometimes we need to consider whether or not we want to break the laws that we've made for ourselves. Specifically, I want to talk about energy. So, renewable energy, we know, it is defined by an act of Congress. Renewable energy, it was made for the IRS for a specific tax credit. So why would renewable energy be used? Well, they wanted something that encompassed technologies that the government wanted to promote. Solar, wind, biomass, biogas, and biodiesel, which were all things that were kind of, all the bios were made from organics that were then a fuel, right? So biodiesel is made from things like food waste, and biogas is made from digestion of waste or by other means. Some of these things were made by crops, beans, algae, things like that. And biomass could be as simple as wood and wood chips. So why would I be talking about that? Well, there are other ways to make power without fossil fuels. But there are issues with those. So what kind of issues are they? I want us to talk specifically about ocean power. Now, there's three types of ocean power that you probably can either guess how they work, or you might even be familiar with them. There's wave power, there's tidal power, and there's ocean current power. So all of those make some sense, right? You have some form of movement. You turn that movement of the water into a movement of a system. You turn that movement of a system into electricity. We call that high grading. So you start with a low grade energy of waves or water moving. You move that to a higher grade of energy of maybe rotational energy. And then you turn that rotational energy into electricity. And that's how you make high value energy. And you lose some of the energy as you go along, right? Not all the power of the wave turns into the mechanical energy. Not all the mechanical energy turns into electrical energy. But those technologies work pretty good, but they have their limitations. Now, I believe all forms of power generation have their appropriate use and platform, but that everything else becomes local. So if we're specifically talking about wave power is pretty good, except for the fact that you don't always have waves. You have to be in the ocean. And you have to be able to take the good and the bad of the waves. Obviously, sometimes you're not going to have waves. That can happen time of day, that can happen time of year, that can happen seasonally, whatever. So that's not helpful. You have to be able to tolerate the ocean. There's salt in the water, there's other things in the water, there's living things there. You have to be able to tolerate all those. The familiarity I have is one of my students I went to college with. They did a research on tidal power, and they found that generically a tidal power generating system lasted between 2 and 5 years. Our ocean wave system lasted between 2 and 5 years because the ocean is really nasty. And so they found that the best thing to do was to not worry about squeezing all the efficiency out of the actual generation of the system, but to make something that was really cheap, you could throw in, it would make a bunch of power, and then when it was done, you'd throw it away. Now, throwing it away is not really a green energy thing, so wave power is not necessarily a great renewable power. Next technology, tidal power. Well, tidal power is pretty good. Tides happen, they're regular, but they're not all the time. They go up, they go down, they pause kind of at the ends. They have to do with the moon. There's seasonal highs and seasonal lows. First problem with that is obviously you still need to be next to an ocean. Next problem is that where the tides tend to be the greatest is where nature's kind of involved the most. Tides are greatest at river outlets, bay outlets, between the ocean and others, so you can get a big transfer of water, transfer of energy. That tends to be where you have the most vegetation, where you have the most wildlife, where you have birds, where you have fish, where you have crustaceans. So it's not a great place to put a power plant. Likewise, yes, we're only talking, it's only on the coast. It's only wherever it happens to be. Then the last one is ocean currents. Ocean currents tend to be more consistent, but they tend to be farther out into the ocean than the tides. So now you have to go to where the current is. You have to then transfer that power back in to where there's people who want to use it. Generally, when we're talking about currents, we're talking about like rotating basically a windmill that's under the water. Nothing bad about that, nothing horrible about that. But ocean currents tend to be also still kind of seasonal. They kind of move, they change elevation and change back and forth. They're not in one specific place. Or you have to go with a big, broader current. And that's not necessarily a great way to extract a lot of energy. Now, I can pick a perfect place to use something like tidal current energy. Like, I'm going to say underneath San Francisco's Golden Gate Bridge. Now, the strait underneath San Francisco's Golden Gate Bridge is really narrow. San Francisco Bay has a large area and not necessarily a large volume, so you get a great current right there underneath the bridge going in and out. Now, that's good for a bunch of reasons. Number one, there's a lot of energy to pull from. Number two, the current is so strong, it's actually stripped out most of the organic material, so you don't have the vegetation there. You don't have the species there right underneath in that strait where you'd want to extract the energy. Now, here's the problem. That tide is so strong, there's stories about people doing 14 knots into the bay and moving backwards because the water speed is so fast. Well, that's great for extracting energy, but if you put a rotating mass underneath that and you now have a pattern of changing the flow through there, it's going to make driving in and out of there on a boat much more difficult. Now, I'm not worried about commercial freighters or military boats. What I'm worried about is the person on a bow cruiser or a 26-foot power sailboat kind of thing. Definitely a person who's in an ocean kayak or a windsurfer, because now that's going to be a really strange, still very fast current going through there. Also, you have the population center there, so you're going to take the power and use it right nearby. You have seasonal and tidal things. It's going to move throughout the day, so you're not going to make all your power with that, but you could make a good amount of power with that. Now, I would say ocean power is not the answer to the United States' power plan or global warming or anything like that. But I do think that there is one technology that we do need to start talking about a little bit more. That is ocean thermal energy conversion. Now, you've never heard of that because you have a life and probably Disney Plus, and you have much better things to do on weekends than research bizarre ways of generating power. So don't worry about that. Here's the new kid on the block, right? Ocean thermal energy conversion. With a fancy name like that, it's got to be brand new. It's got to be like, uber new, right? We call it OTEC, right? It's got a catchy, tag name, hashtag OTEC. So how old is ocean thermal energy conversion? What is ocean thermal energy conversion, and where should they have ocean thermal energy conversion? I'm going to specifically think about North America because it's where I live. And ocean thermal energy conversion works off this concept. If you have warm surface water, cold deep water, you can just bring those waters closer together and you can drive a system that will make power. Now, usually it works off some type of principle, either like a Stirling engine which the hot keeps pushing on the piston and the cold keeps pulling on the piston. And as long as you have a good going flywheel, you can run that thing forever as long as the hot stays hot and the cold stays cold. You can do that. There are also other technologies, but this is kind of how engineers look at this. We look at the potential energy of the high energy side and the potential energy of the low energy side. We look at the difference in those, and then we multiply it by the mass flow rate, and that's the most energy we could use through there, right? So you're looking at temperature in pounds, basically, for what we're talking about. When we do this with steam, we use the high temperature to make a pressure. Same with gas turbine plants. So you have a thing that's hundreds to thousands of degrees, you run that through, and then it comes out the other side, usually high hundreds of degrees. And that change in potential you use to turn something like a steam turbine. That turbine turns the thermal energy into mechanical energy, and then you turn a generator or an alternator and you make electrical energy. That's a good way to do it. And in fact, those systems are very good and very efficient, and so you probably have one not too far from where you live. They can run without stopping. They can ramp up and ramp down a little bit fairly quickly, like in less than days. Depends on your heat source. And they usually are on the order of 30 to 40% efficient. So 30-40% of the BTUs that you put into that hot side turn into something like electricity or a usable heat. If you can't get quite into the thousands of degrees, you could use something like an organic Rankine cycle turbine. Now that would use like a refrigerant or a working fluid that I would think of as a refrigerant, because that usually boils off with the heat, makes pressure, and then condenses back into a liquid on the other side, like an air conditioner backwards. So if you could take your air conditioner and just put hot on one side and cold on the other, and if that would generate the pressure and then spin your motor with the temperature change, it would make electricity. I have a little bit of familiarity with one. The one I know of used 500 to 700 degrees in and then 300 to like 100 degrees out. And that was like in the 20s of efficient. So if you put in, $1 million, you got 200,000 worth of energy out. That's still pretty good, especially if you're not paying for that source of heat that's going in. So if you're burning stuff for something else, you can take the heat from that burning stuff, feed it in there, and make a bit of energy. You could use something like that also for an OTEC, but you'd have to find a pretty good one, because here's how the numbers start to work out for that. Normally you're looking at hundreds of degrees of temperature change. That's a lot of potential energy. When you're dealing with the ocean and you're dealing with like one fixed point in the ocean, the warmest your surface water gets over a year average would be in the 70s. The temperature of the deep water is going to be 34-ish, because that's the most dense the water gets. Now what's making it 34? The weight of the water on top of it. So you just have to get down to where the depth of the water dictates that the temperature of the water be 34 degrees. So then you take that water, you bring it up to the surface through a bendy, flexible hose tube kind of thing, and it comes up to the top. You then have it use that as your cold side of your plant, and you use the surface water as the hot side of your plant, and then you kind of like squirt the rest out the back. So you're bringing in warm water and cold water. You're spitting out water that's in between that, and you're making power. So what could be wrong with this? Well, the first thing is I'm alluding to the efficiency. It's about 4% efficient. Yeah, it's really not great, but it uses water and it makes water. That doesn't seem that bad. You get a big surface of kind of colder ocean water. That could be a thing. It could not be. And so you get 4%. How do you make any kind of usable power? Well, you make usable power by using a lot of water, like millions of gallons an hour. Yeah. Oh, yeah. You only have 40 degrees, whereas you had hundreds of degrees. So you just up all your pounds so that it works out in the back that it comes to something usable. So how big are these things? First of all, when did they come from? So the first notes of talking about this type of a system come from about 130 years ago. Late 1890s, they were talking about using it to make mechanical energy to drive things like mills, like we used to use water wheels. We didn't care about electricity. Electricity was this weird thing people were going to start using for cars in a few years. And that Edison guy was going to use it to do something to an elephant and make some light. So they were just making mechanical efficiency with it. We then did a demonstration unit. We did one scaled down to test, and we put it in the ocean and we ran it for a while to see how it would actually work. That one was put in Hawaii right around the time it became a state. Late 50s, early 60s. And how big was it, right? This one was scaled down. How big are they normally? Well, the scaled down one was about 65 kW. Now, average house connection is something about 5 kW. That's like about a 100 amp, a 50 amp connection for a house. 50 amps at 115 volts. It's about 5 kW. Usually the biggest thing in your house would be about 5 kW. Usually it's a water heater or a really big electric range or air conditioner or something like that. So you could power, what is that, 13 houses off this thing? Okay, that seems about right. So how big is a big one, right? A big wind turbine that you can buy pretty easy is about 75 kW. Bigger ones are like 100, 150 kW. The big utility ones that's turn really slowly, there's like a megawatt. A big solar array is like a megawatt or two. This system that runs on water, the generic design size for those, kind of upper max, but what people usually want is 500 megawatts. Yeah. And if you go on the Department of Energy's website, I don't know if it's on the EIA side or whatever, you can actually look up the power plants near your house. Chances are pretty good that the biggest one near your house is going to be right around 500 megawatts. That's a good size nuclear plant, gas steam turbine plant, combined cycle plant. That powers something like 100,000 households. So that's like call it 500,000 people. Wait, we could power 500,000 people off ocean water? Yeah, it's not quite that simple, but yeah. Well, but like, does it go all the time like the steam plants? Well, as long as the deep water's cold and surface water's warm, it should. So why don't we have them everywhere? A handful of reasons. First reason is because it takes an ocean. So, Kansas, sorry. The next reason is because it needs deep water. And so if you look at the United States, you run into a bunch of problems really quick, right? If you go to like LA, the problem you have is your surface water tends to be colder because it came from a ways north of you. So as you bring that down, it's about 10 degrees colder. Could you still do it? Yeah. Is it still worth it? Take a lot more water at 30 degrees than it does at 40 degrees. But still a potential. You could do that. The problem on the East Coast is you don't really get the deep water with the user base, right? When you talk about like New York, DC, Baltimore, the Atlantic shelf goes out. And so you have to go out a good ways to get deep enough water to get that cold water. What you need is some place that's near really deep water with warm water with a population base. You need like a tropical island with a couple million people on it. Some place that's maybe near the Puerto Rico Trench or the Hawaiian Islands. Side note, Puerto Rico and Hawaii make the base load of their energy using distillate, oil. number 2, number 4, number 6 in Puerto Rico, Bunker C if they have it, and diesel. And they run their power generating stuff usually off that. But why still don't we have them everywhere? Well, this last one would kind of be counterintuitive. When they do hydroelectric dams, we stop doing big ones. And we stop doing big ones for a pretty simple reason, and that's that they change stuff. If you research the Hoover Dam, when they put in the Hoover Dam, it changed the river downstream of the Hoover Dam quite a bit. And not necessarily all for the good. But if you go look at the Glen Powell Dam, it was this weird, muddy, whatever seasonal thing. And when they put in the Glen Powell Dam, you got a pretty good lake just above it, for those of you in Arizona. And you actually started seeing more fish varieties in the downstream part of it, because having the controlled seasonal flow stopped the flooding of the banks and the silt deposits and pick up, and it wasn't as muddy anymore, and it wasn't as problematic. Now they're having other issues with the Glen Powell Dam. I don't care to talk about those. But it just has to do with the fact that all that mud still exists. It's just showing up in the lake and other spots, and they don't have a great way to shoot that downstream. So why don't we do those anymore? Can't we go figure out where the good ones would be? Well, here's the problem. The Environmental Protection Agency doesn't care if you're doing good or bad. It cares if you're changing what's going on there. So, what happens with OTECs? Well, you take that deep water and you bring it up to the surface, you mix it, you shoot it out the side. And now we're not doing anything. Well, we're changing the surface temperature. Yeah, it's going to be significantly, but just for small. Well, millions of gallons, but 8 acres of what? Maybe a square mile? I don't really know. Haven't done that math. So you're going to change the surface temperature. You're going to lower the surface temperature of tropical water. What does that do to the critters? Oh, well, we know because they did that one. And it brings the nutrients from the deep water up to the surface and spits that out. Does that change anything? Oh, yeah. You get like a bloom, like an algae bloom, plankton, and all kinds of stuff. Oh, how do you fix that? You can do nothing, or you can stock it. What does stock it mean? Oh, if you're a fisherman, you know that they take little fish and they put them in like rivers and creeks and streams, and then you get big fish in the bigger rivers and creeks and streams. Oh, yeah, no. So what happens when you start pulling the deep water up and blooming and you get the algae and you get all those other things is you get localized pockets around your OTEC of fish. And in fact, one of the problems they had was sharks and whales. If sharks and whales are problems. So you create a new ecosystem around the OTECs. And they started throwing some fish in there, and the fish would stay and grow more fish. And then the things that eat fish would come and eat the fish. So is that a problem? Well, per the EPA, it's changing the ecosystem. So the EPA said, no go. People said, well, we could farm the ocean now because we can grow stuff that fish would eat, and we could grow fish, and the fish won't just like come, eat, and then swim away because they'll have to swim miles and miles and miles to get a similar ecosystem. So once they get there, they kind of stay there. We could farm these fish. We could catch these fish. We could make power, and we could farm fish, and we could create more life. So the EPA basically said no go. I don't have any problem with the rules that we don't make. But when we make a rule like that, if our goal is really to use less fossil fuels, we should probably figure out how to do something like this. Now, who would do something like this? That's a better question. Because now you need someone who's not for fossil fuel power, who's for making power with natural sources, but is going to fight the EPA, and we're going to have somebody build all this stuff, right? So who's going to build all this stuff? It's going to be someone like GE, Pratt Whitney, McDonnell Douglas, Lockheed Martin. It's going to be a big government contracty type private entity. And then who's going to run it? Who's going to buy the one once we make it? That's where it gets really sticky. Because if we were doing this 40 years ago, maybe in the 80s, there'd still be a chance that we'd be selling it to, Miami Power Generating Authority or the city of whoever power company. But we don't have those anymore. We have National Grid, Keyspan, ComEd, ConEd, PSE&G. We have these little private or private-public cooperatives or private-public joint ventures where someone's going to make money off this thing. And because we're going to need a private company to make it, we're going to have a private company run it and make money with that. Whoever's going to come and change the laws that we've made is going to have to know that they're going to be benefiting private companies. So they're probably not going to have an R, or probably not going to have a D after their name if they're going to benefit a bunch of private companies. And they're probably not going to have an R after their name if they're going to have to go against fossil fuels and do something crazy. The only type of people who would do this would be a green power guy who wants to pick on the EPA, which honestly could be the guy we have now or the guy we might have later. You need someone who's willing to go to bat for nothing to get something like this done. So, why am I saying this? Because a lot of times you need people to start asking these types of questions to figure out if our laws are correct. Do we want the EPA to prevent things like this from being built, given that we know what the alternatives are? Right? We're going to build a combined cycle gas plant. It's going to run on natural gas. We're going to build something like a nuclear plant. We're going to build something like trash burning power generation. Now, those have their places. They have their uses. But they might not be the best answer. So, for Adding Energy, I'm your host. Thanks for giving a watch.